All right, line A1, learning test number 14. We're going to go and take a look at solving DC capacitor problems. And before we even get around to solving anything, we have to talk about how do we apply capacitors in series versus capacitors in parallel. Right underneath this figure inside of your binders, you're going to go and see a whole pile of other components that are going to be placed inside their formulas, where they're just going to go and talk about how, it's some of all voltage drops, etc., etc., etc. And they use that to go and define what is happening inside of my capacitor, my series connection of capacitors. First of all, before we do anything else, we're just going to go and take a look at my DC supply. We'll change that around, put that into the proper polarity. And now that we've got that into the proper polarity, because we've got polarized capacitors over here, we'll look at what happens when we would close in on a circuit like this. We know that inside of our battery, we are going to go and have some sort of a charge separator, right? It's going to be a chemical, an electrolyte that's inside of there. That chemical is going to go and strip electrons, move them over to the negative terminal of the battery, and then it's going to go and push the positively charged atoms over to this side. We call the positively charged atoms that are missing their electrons, we call those holes. These ones are going to be my electrons. As soon as we place a circuit across like this, what happens is that my battery then says, look, I got all of you electrons over here. You don't like each other. Like charges repel. Get out of here, spread out, find some more room. And so we create the circuit. These electrons are going to go and travel along here, and they're going to start to build up on here. Now, we're not going to build up a ton on here. I'm just going to build up 3 right now. They're representative of millions of electrons, but we'll just build 3 up onto there. For every action, there's an equal and opposite reaction, right? Newton's third. So that means that if I store 3 electrons on here, that is going to go and distort my orbitals in between, which is going to go and push away 3 on the other side. So 3 on the other side are going to get pushed away. Those 3 end up over here, which once again is going to go and distort orbitals, which once again is going to go and push electrons away from this side. And those 3 electrons that get pushed away end up there. One last time, we see distorted orbitals over here, and we see that, drew that one there as electron. We have 3 more over here, and therefore we're going to go and have all of these that are, we're going to have our current flow that's going to go through here. When we close in, there's going to be that brief instant where we're going to go and see our currents is going to go and spike and then taper away, and as the current spikes and tapers away, the voltage over top of the caps is going to go and rise like that. What you'll note about it is that the Q, the amount of coulombs that I'm going to go and put into here, is split up now across 3 separate capacitors, right? We know that C is equal to Q over top of V that I'm going to go and have. So if I say that, each of these 3 capacitors over here, instead of me having them utilize to their full potential, really I'm only storing some electrons, the coulombs of charge over here, over top of 1/3 of my voltage that I'm going to go and have. Which if I go and take a look at my capacitance, it's going to go and drop my overall capacitance of each one of these, right? Because each one of these is now only getting 1/3 of their value of voltage and coulombs, etc. Really what we're seeing all the way across this circuit is that we store the same amount of coulombs as what I would have on any one of these, but what we have seen increased is the amount of dielectric that's in between these, right? It's a chain reaction, electrons to holes, electrons to holes, electrons to holes, etc. all the way through, but now we've just got a thicker dielectric that's going to be seen across here. We know that, once again, C is equal to 8.85 times 10 to the negative 12 times K times A, all over top of distance. And if my distance between effectively has tripled for the same number of coulombs of charge that I've stored on there, basically that would be the same as if my capacitance overall has dropped over here. The long and short of it is that when I am connecting capacitors into a series type of configuration, what I'm going to see is my CT, 1 over top of CT is equal to 1 over top of C1 plus 1 over top of C2 plus 1 over top of C3. Note that the way that we add in a capacitor, series set of capacitors, is the same way that we add in a parallel set of inductors. That is the inverse method, right? Once again, as we've said before, capacitors and inductors are going to be polar opposites in a lot of what they do. How do I punch this into a calculator? Well, the easy way to go and punch that in, if I want to get my total capacitance of the circuit, CT, it's going to be equal to bracket C1 to the negative 1 plus C2 to the negative 1 plus C3 to the negative 1, and then all reinvert it once again. That'll get you your total amount of capacitance that you would have for each one of these. Try it on your calculator. Put in a value of 3 farads for each one of these, and if you put in a value of 3 farads for each one of these, what you're going to find out is that when this thing spits all the way through, you're going to be down to 1 farad for that whole grouping. All right, capacitors in parallel. Capacitors in parallel are going to go and have the same value of voltage that's going to be stored across them. And we are now going to go and see this section. This is V is equal to Q over top of C. Right? It's the same as our C is equal to Q over top of V. We've just reworked that formula over there. What we see when we put capacitors in parallel is that we are going to go and have an increase of our plate. Let's just fix that battery first. We're going to have an increase of our plate because I'm going to be able to store my 3 onto here, driving 3 away from here, back to the source. I'll store an additional 3 over here, driving away their 3 back to the source, and store an additional 3 over here, driving away their 3 back to the source as well. And what I see is that I have gone and tripled the amount of Q that I'm going to go and have across there for that same value of voltage, right? Still the same value of voltage. If I only had 1, just pretend like you cut off that circuit like that, I would still have the same value of voltage, but now I've got 3 of them, and I'm storing 3 times the amount of charge. What we see when we add capacitors in parallel is it's got the same sort of effect as if I went and increased my plate area. So for me to go and add these things that are going to be in parallel, all that I need to do is just add them together straight up. CT is equal to C1 plus C2 plus C3, etc. Easy enough to go and add these up. If you would go and take a look at the same circuit that we had there previous, where we said we had 3 farad capacitors, and you'd add them all up, you'd see that this would go and give you a grand total of 9 farads. Really, once again, it is just the opposite, or it's the inverse of what I would have from my inductors. Just remember that these things are always acting opposite to each other. Okay, let's move on to doing a couple of capacitance problems, and we'll just drop them right onto the existing pictures where they work with those. So give me a second, I'm just going to go and clear this one off. As well as I will clear this one off. Perfect. Let's move into those questions. So our very first problem has 3 caps. I got a 5 microfarad, I've got a 10 microfarad, and I have got a 20 microfarad cap. They're all going to be connected into series. And then they want to know what would the total equivalent capacitance be. First of all, I should be able to recognize that, look, if I'm going to be doing that inverse formula, my overall capacitance of the circuit is going to end up as being smaller than the smallest of my capacitors. So before I even start that, I know that I'm looking for something that's going to be much smaller than this 5 microfarad. What I'll do is I'll punch it into my calculator using that same formula that we had there before. CT is equal to bracket bracket C1 to the negative 1 plus C2 to the negative 1 plus C3 to the negative 1, and then, like I said, that second bracket there, I'll reinvert it like that. So I'll just punch that into my calculator over here. Bracket 5 and to the negative 1, mine is up here, yours might be down here over top of the 2. 5 to the negative 1 plus 10 to the negative 1 plus 20 to the negative 1, or the inverse, and then I reinvert the entire thing, and it kicks out a value of 2.85. This definitely satisfies the idea that it's going to be less than that. This makes sense. What they're doing on theirs is they are just going and adding together all of the bottoms off of theirs to go and form that, 1 over top of CT. So they're going and adding in 1/5 plus 1/10 plus 1/20 to go and equal this, 1 over 0.35 that they have over there. The math doesn't make sense the way that they present it inside there. I'm not too concerned about trying to correct their math, though, because this is the way that we do these things on a calculator. We punch them into the -1 to the -1 to the -1, and then we re-invert the entire shooting match. So this one would become 2.85 that I'm going to go and have for it. Okay, the next one that they have is it says total capacitance for a series circuit containing 2 capacitors is 20 microfarads. If that's what my total capacitance is, if the other one of them is a value of 60, what is the value of the other capacitor? So in this case, we're only going to be looking at 2 of them. We'll just white this one out over here, and we will pen in around it. Beautiful. So we know that we've got a total of 20 microfarads, and we're looking for what we're going to have if this one here is going to be 60 microfarads over here. Once again, if you're given this ever on an exam, you punch in the 4 answers to go and double check it. But if in the case like this, you need to actually go and calculate it, you will have to go and work these things to that common denominator that they're going to go and show. The way that you're going to work them to a common denominator is you're just going to find a number that they're all going to go and work with. Now we know that 1 over top of CT is equal to 1 over top of C1 plus 1 over top of C2. What we don't know yet is we don't know what C2 is. We know what C1 is over here, so we'll just subtract C1 from both sides of the equation. When we do that, we're going to end up with 1 over top of CT minus 1 over top of C1, which is going to be equal to 1 over top of C2. Now we'll drop in some values. CT we know is going to be 20. C1 we know is a value of 60 over here. And we don't know what C2 is, but what we can't do is we can't subtract 1/60th out of 120. So what we're going to do is we're going to convert this one to 60th. So we're just going to multiply that one by 3 over 3, which is the same as 1, which would tell me that I'm going to go and end up with 3 for the top and 60 for the bottom. So 3/60ths, which is the same as 1/20th, minus 1/60th would obviously give me 2/60ths. And if you would go and take 2/60ths, you can go and divide both the top and bottom by 2, which would take you down to 1/30th. And if that's what I have out of all of this, 1/30th, and if that's going to be equal to 1 over top of C2, then therefore my C2 must be this value over here, 30. So it would be a 30 microfarad. You can go and do your double check off of that one to make sure that it verifies out. Example number 3 talks about capacitors that are going to be connected in parallel. It says where I've got a 20 microfarad capacitor that is going to be connected in parallel with a 30 microfarad. And then what is the equivalent capacitance of that circuit? Let's wait this one out because it's not being utilized. Well, it's pretty simple for these ones. We just go and add our capacitances straight up. 30 microfarads plus 20 microfarads is going to bring me out to a value of 50 microfarads for that one. Example number 4 says what value of capacitor must be placed in parallel with a 60 microfarad in order to go and get a grand total of 90. So if we already have one, that's going to be a 60 mu f over there. And we're looking for a grand total of 90 out of just 2 capacitors over there. Just subtract your 60 out of the 90. It's going to tell you that you would need to go and have a 30 for that one. They're relatively straightforward calculations, the type of calculations that you've been doing with inductance and with resistance for quite a while now. Should not be blowing your mind yet with these. That whole concept of trying to go through into the common denominator, still takes a little bit to get back into, but I'm sure you'll get back into it. If not, once again, there's that trades math module that has been posted up on your Blackboard shell. Go into there, read that trades math module, and figure out how to do these. Time constants, we did talk about tau, that we're going to be able to go and create a new form of tau, which is going to be my RC. And we're going to hear that term RC timing circuit, or resistive capacitive timing circuits, that we're going to use for all sorts of electronic applications. My RC is only going to give me a single time constant that I'm going to go and have. If we want to go and get to our full value of charge, then that is going to have to be done off of 5 time constants. If we want to get to our full value of discharge, that would have to be done off of 5 time constants as well. Let's identify what these two curves could be used for. Let's start with this one over here, the one that's highlighted in green. This curve describes my voltage charging Okay, it's just going to be the way that the voltage rises up. This one over here can be used to describe 2 separate things. It's going to be able to go and describe my voltage discharging. We start out at the 100% voltage and we drop it all the way. As well as this one is also going to be able to go and describe my IR, the current that goes to the resistor that's in series with our capacitor when we are charging. As well as it's going to be able to go and describe my current that I'm going to be sourcing out of here. Initially, I'm going to dump a boatload of current out of here. IR discharging that we'll have out of it as well. And that's for just a simple series type of circuit where we've just got a switch, where we have got a resistor, and where we have got a capacitor, like that. We're following this yellow curve. This yellow curve shows that when we close the switch, we're initially going to have a big dump of current that's going to go through this thing, but then that current is going to go and taper off to a value of 0. And when we go and discharge, we're going to have a big dump of current that's going to get pushed out of this thing, and then it's going to discharge off to 0. I guess you could actually even use this yellow curve to describe your voltage across the resistor during charging as well. But we'll leave it, with just looking at these currents and where our voltages themselves are. Now that we know where our currents and voltages are, let's go and take a look at how they're going to go and graph out. Next couple of pages actually just are going to be going over the same thing. They talk about this 0.632 and they talk about this 36.8. The 0.632 and 36.8%, those ones are just going to be complementary values. Together they're going to add up to become 100%. When we're raising, we raise 63.2%. When we're falling, we drop 63.2% across each one of those. This one over here shows me my charging voltage and discharging voltage, the same way that we just identified them on the previous one over there. This one over here is going to go and show me my voltage of the capacitor. That's this EC, stands for capacitor, not charge. The voltage of the cap is going to be dropping. As the voltage of the cap is dropping, it's going to be pushing its current back out. Remember how all that current came into the capacitor in one direction, right? Like if we had our cap that was, whoa, that's not a cap over there. But if I've got my cap like this, when we are charging up that cap, we had all of our electrons flowing in like that. When we discharge, it is going to go and send them out in the opposite direction, which means that their value of voltage would be in the opposite direction. Use your left-hand generation rule. And if you flip around your middle finger, you're going to see that you're going to be looking at an opposite direction if you need to verify that. That's why this one over here is shown as being on the bottom, that at the instant that my cap starts to discharge, it is dumping electrons into the circuit in the opposite direction, which means that it is going to be generating an opposite polarity of voltage over top of any load that is going over top of that. Underneath the drawing that they show for that one, they do talk about, that capacitors inside of the Canadian Electrical Code. We covered that. We looked at, that we need to have these things discharged underneath 1 minute if we're going to be underneath 600 volts. That's going to include pieces of equipment like variable frequency drives and stuff like that. Generally speaking, I still don't touch them for about 5 minutes. And usually by the time that you found the panel, turned it off, and made your way back there, it's usually going to be a couple minutes anyways. But always just, know that a capacitor stores charge, and if you don't allow it to discharge before you start working on it, you're going to be the path for that discharge current to go through. It's an uncomfortable thing, taking electrons through the skin. Anyways, just be safe. RC circuits that are made up of resistors and capacitors, are going to be used for timers. Now, they talk about, how we can use it for an alarm panel and stuff like that. We're not going to use them for alarm panels this year, but what we are going to do is we are going to go and use them to go and charge up and discharge electronic components inside of particularly our third year components. We'll see it a little bit here inside of second year, but most of it's going to be inside of third year. Let's go over to this final picture that they have over here, they're showing us this example. We should be able to identify which one of these is going to be my charge path versus which one of these is going to go and be my discharge path. And we should be able to go and graph out what our current looks like over top of time. And that's what all the questions around here are really dealing with. So the first one that they ask about is, how long is it going to take for us to go and bring this cap up to its source voltage? Well, if we start initially with our switch in the open position, we would have had 0 volts over top. As soon as we close, we know it should be taking us 5 time constants. So if it's 5 time constants, we need to examine which resistances do we use. Do we use this one? Absolutely not. There's no current that's going through it, so it's dead to our circuit. What we are going to be using is we are going to be using this path, because we see that we're going to deliver electrons from here to this. When we deliver those electrons to here, they're going to bump electrons away from the other opposite side over here. Tau is going to be equal to RC, so tau is equal to RC, 200,000. My C is going to be 20 microfarad, so we're going to go 0.000, this is milli, and then this is going to be micro, 0.2. So we're going to multiply together 200,000 and 20 billionths of a farad that we have over here. When we go and multiply those two together, basically all of these decimal points cancel out to all of these decimal points over here. You could do this by, putting these in as being 10 to, the power of, etc. Or just punch them into your calculator in the full units if you're unsure how to go and do that. When you do so, you're going to come to a tau that is going to go and be 4 seconds. So it's going to be 4 seconds for a single tau. Now remember that it takes us 5 taus, so we have to go multiply that by 5, which means that it's going to go and take 20 seconds. So if I wanted to, I could go and graph this thing over top of 20 seconds. We'll just do that really quickly over here. We're going to go and say that this is our value of voltage. Here's where we turn it on, and that we are going to go and graph this thing, and right there is where it hits that 5 volts, and this is going to be my 20 seconds. That 20 seconds is just going to be used for a timing purpose. For whatever we place inside there, usually we're looking to go and hit a trigger level. If something did not trigger until 5 volts, this would be the way that we would figure that out. The next example they ask is, what's this thing going to be after 4 seconds in the above circuit? So, what would the voltage be after 4 seconds? Every 4 seconds is going to be a single time constant, so we're going to be rising by 0.632. Inside of your book, they show this thing as being 3.16. That is a single time constant that they are putting in on that book. It's errata under example number 2. Don't trust it. Let's go and take a look at our graphs. If we go and take a look at our graphs, and we did document these on the other one, we know that the very first time constant we raised to 63.2%. Then we know that by the middle one, we are at 95. These are the important ones that you need to know. And then by this one here, you're going to be at 99.3% that we are going to be inside here. If we take a look at these, we can also figure out the ones that are going to be in between here. This is 0.632 plus 63.2% of 36.8, which is going to get you to, I forget what this one is off the top of my head, because I don't have them all memorized as well, but we can quickly go and do that. So 0.632 times 36.8, which gets me to 23.25 plus 63.2, which gets me to a value of 86.5. 86.5%, and then this last one over here is going to be 98.2. That one I do have memorized. I don't know why I just wobbled on that one, but it is what it is. So 4 time constants into here, we would be at 98.2% of our voltage that we are going to go and have. So it says, what would the voltage be across the capacitor after 4, oh shoot, whoa. My bad, I read the question too fast. Some of you do the same thing. This is why, it doesn't really upset me that you read questions too fast because I struggled with the same thing. I read 4 time constants. Let's go back into example number 2. It says, what would the voltage across the capacitor be after 4 seconds? 4 seconds is a single time constant. All of this that we just did here, establishing these, we don't need that for these. We're only looking at a single time constant, which we know is 63.2%. So yes, the book math is correct inside of here. My apologies, I just read that one way too fast. If we did need to know 4 time constants, then we would go and use this value, 98.2% of our 5 volts. But that's not what they're asking, so let's maybe not do that. Example number 3, they say when the switch is transferred to the discharge position, what will the voltage be across the capacitor after 1 time constant? Well, after 1 time constant, we know that we are going to have dropped down to this point, 36.8%. So we can just take our 5 volts and we can go and place that across that 36.8% that we are going to have over here. So run that through and around like that. The next question they ask, example number 4, is a little bit more complicated. They're asking how long does it take to drop to this level? Well, to drop to 1 time constant, we would need to go and analyze this circuit based upon what our RC is. Remember how we developed this RC before? That RC was based on the entire circuit that we had based upon this 200,000. But now what we've done is in our discharge, we've changed the value of resistance to now become 10,000. And so if we go and take that 10,000 and we multiply that by 0.02, or by 0.000002, what we end up with is we end up at 2 seconds. 0.2 seconds that we are going to go and have for our single tau that we're going to have over there. If that's going to be a single tau, we know that we can multiply that by 5 to go and find what it would take for this thing to fully discharge. So if you take 0.2, multiply it by 5, you're then going to go and end up at 1 second for this thing to be fully discharged. This means that if I were to graph this, my discharge curve is going to look like this. It's going to be so rapid, that it's almost going to go and appear to be instant. Like that, and then we would go and have another charge, over the next 20 seconds, and another really quick drop. It would form a really, really good sawtooth type of voltage that we could utilize. All right, that covers us off for CAPS in DC. Make sure you go through all of the learning tasks and questions off of these ones. Go through your BCIT book. At this point, this is the last of our DC analysis, our DC theory on these. We're now going to move into putting these things into AC. So it's going to be a completely different frame of mind that we're going to have to set up.